Okay. So it's not like this.
Yeah.
Hello? Oh, yes.
Yeah.
Okay. Well, so I'm the chair of PPDP. Thank you very much for attending PPDP. Okay. We have 13 presentations, the regular papers during these 2 days. We have 2 invited speakers, Delia and Maribel. Okay. For the talk of Maribel Fernandez tomorrow, it's going to be in another room, the room of Lobster. Okay. And there's a problem in the program where it says that Maribel is going to be in 2 places at the same time, okay? So just be aware that she can be only in 1 place and it's going to be in Lobster, the other room, okay? And we have also a paper today about the 10-year award. So I'm not so sure if the speaker is here, okay? I will look for him, okay? So it's the other activity that we have, okay? And Michael Janus is going to chair this first session with 3 papers, so thank you very much, okay? And I think that's all, so thank you for attending, and I hope you enjoy PPDP, okay? And remember that all the talks of all the events are going to be recorded, okay? So when you have questions, just wait for the microphone, okay?
Okay, thank you very much for the introduction. So I'm Michael Janus, and I will chair the first session, and we already see here the title of the first session, Calculus of Delayed Reduction, and Emma will present the paper.
All right, thank you. So our calculus is called the Calculus of Delayed Reductions, and this presentation will be about this. It's an extension of call-by-push value. Call-by-push value is a calculus designed by Paul Levy. The basic theory of this calculus is that we distinguish terms into 2 distinct sets. Computations, something that does, and values, something that is. It was originally proposed to model the call-by-name and call-by-value sections of the lambda calculus, but it doesn't actually model small step semantics correctly. Instead, we present CDR, our calculus of delayed reductions, which can be seen as a simplification of call-by-push value, which changes how substitution works. We will show in this presentation that we can interpret call-by-name and call-by-value into our CDR and show that reductions and types are preserved. We also introduce Herbulin and Currian's lambda-bar-mu-mutilde-calculus, and we can interpret our calculus of delayed reductions into that, motivated by its natural modelling of call-by-name and call-by-value. First off, a quick refresher on the lambda calculus and call-by-name and call-by-value. Lambda terms have this subset called values, and then just regular terms. You'll notice that these values contain variables and abstractions. We'll call these lambda values from now on to distinguish between these and other calculi's definitions of values. Beta reduction just contracts an abstraction and an application, and in the regular lambda calculus, we can reduce everywhere. Call by name restricts the contexts to just the left-hand side of an application. This can be seen as lazy evaluation, where we don't evaluate the argument before applying it. And call by value reduction reduces on the left-hand side of an application, then the right-hand side. Notice that we can only beta reduce when the right-hand side is a value. So this can be seen as a kind of form of strict evaluation where we evaluate the argument before we pass it in. Call by push value is an extension of this lambda calculus. So we have these variables, these abstractions, and these applications. But we also have some extra syntax. We have this thunked computation, which is what these curly brackets are around in a value. We can have a forced value, which is what this bang does. We can return a value, or we can sequence 2 computations together. Notice that these values, this distinct set of values, are not lambda values. The abstractions here are actually considered as computations. The reduction rules are as follows. We just have our regular contraction, which by design and syntactically has to contract values, because you can't have a computation on the right-hand side of an application. We have this unblocking, this forcing of a thunk, and then we have this returning or forcing, where if we sequence a returned value next to a second sequence computation, we substitute it in. So essentially, sequencing reduces computations until they are returned. Valuation context, we can reduce on the left-hand side of an application and in the first sequenced computation. We can only reduce computations and never values. Notice here that thunking itself does not actually halt reduction. By the reduction rules and the contexts, we can never actually reduce anything where a thunk could be anyway. We never reduce a value. So we can never reduce on the right-hand side of an application, we can never reduce underneath a ret, and we can never reduce, basically those, and we can never reduce under a force either. So actually, all thunking does is kind of syntactically mark where values are, change a computation into a value. It doesn't actually affect reduction in any kind of way itself. And in fact, even more than that, it's more just something to give us these distinct sets of types, these type markers. The call by push value types are a bit more interesting. We have these syntax markers U for value types and F for computation types. Other than that, we have regular simply typed lambda-calculus type variables and arrow types. Notice that these arrow types, by the definition of how an application works, we have to have a computation on the left and a value on the right. So we have value type to computation type. We have a context of variables, but these have to back to value types because variables can only be values. And we have all our type assignments. We have our regular axioms, our regular applications, and our regular abstractions. Thunking, you see here, doesn't take anything else other than just a computation type A and shoves a U on it, just as we shove it into a thunk. We have our forcing, which just takes a U and pops it off, which is exactly how it would do an unblocking here. We have a returning, which just shoves an F on, but the sequencing here is what makes the returning a little bit more interesting than the thunking here, because it actually has some kind of interesting semantics to it where we have to pop the X into the typing of N in the second sequence. So more importantly, we want to interpret the different reduction strategies of the lambda calculus in call by push value. For the call by value lambda calculus, what we do is we return our lambda values, our variables and our abstractions, and then in application we sequence the first computation and then the second computation. And because of the typing, we have to then force X in the third sequenced computation. This is kind of a shorthand for sequencing multiple computations together. If we can't have X, Y just regularly, because that doesn't fit our syntax of a computation on the left-hand side. Which also is why we can't return just a lambda, because lambdas are computations in call by push value. So we actually have to thunk that. And we have to use the returns here instead of just returning a regular lambda, because that is a computation type, because then we would never halt reduction in our sequencing. Unfortunately, this is only respected by equality in reduction under call by value in the lambda calculus. So basically, if you have a lambda term that runs under call by value to another lambda term, the interpretation of it runs to another value which the original, sorry, I'm not explaining this very well. So we have a lambda value m that runs under call by value to a term n. Then the interpretation of m might not run directly to n. It might run to a term that n will eventually run to. So it might, the reduction of the interpretation of m might not reduce into n. Call by name is in fact even more complicated in how it's related. The call by name interpretation of lambda terms and call by push value by Levy forces a variable, just returns a regular abstraction and just a regular application with the thunk marker on n. This doesn't use return or sequencing. It looks very, very similar to how the lambda calculus is actually structured. However, this doesn't actually respect reduction at all. Consider a self-returning term, lambda x.xx applied to itself. The interpretation of this is lambda x.x bang thunk applied to the thunk of x bang, which, if you reduce it twice here, you get this explosion of force-in thunk pairs. And this will just keep reducing and exploding into force thunk pairs. And because of the evaluation context, we can never reduce any of these force thunk pairs. We have to keep applying it, and it will just completely explode. So what Levy does is he adds this other interpretation rule, which means that we can relate any lambda term to itself with any number of force thunk pairs on top of it. This is the new interpretation, allows reduction, or allows us to interpret, essentially, we have the interpretation of a term can reduce to anything. If a term reduces under call by name to another term, then their interpretations may reduce to each other, to any element in the set of its interpretation. But fortunately, this means that the interpretation is not even a function, it's a set of equivalence classes. It's just a relation, which is a lot less powerful than a function. So our solution here is to change term substitution so we don't get this explosion of force thunk pairs. Our calculus of delayed reductions is call by push value, essentially, but we prevent any forcing of thunks or thunking of forces. So here, the changes we have to our syntax is that we can't have a thunk of a forced variable, and we can't force anything that isn't a variable, because other values are just thunks. Substitution is changed so that we automatically reduce force thunk pairs in the substitution itself. So if we have a forced variable and we want to substitute a thunk term in it, we immediately strip off the thunks and the forces. This means that we can remove our unblocking rule. And evaluation contexts are before. This won't actually change any of the reduction strategies any of the reduction in call by push value, because as before, thunking here doesn't actually change reduction itself. It was just the evaluation rules and the contexts that affected how reduction works in call by push value. So this itself isn't going to affect how any terms can reduce. Type assignment here, we optimize a little as well, because we know now that we can never force anything but a variable, and we can never thunk anything but not a forced variable. So here's where the money shot is. We have call by value and call by name. So the original Levy's call by name has all these returns, but this has only respected by equality. We use pattern matching instead to make it actually respect proper reduction. So we pattern match on the left-hand side of an application for lambda values. And if we have a lambda value, we can immediately just remove part of the sequencing. Because if we had Zn and we interpreted it in Levy's, then we'd have x equals the return of z and y equals n, which we could immediately reduce to this. But so instead, we just immediately return this. And the same with lambdas. Call by name, Levy's interpretation preserved the structure of these, but didn't do any kind of pattern matching or optimization on this, which we do, just considering that the right-hand side is a variable. So this essentially means that we have to do this so that we don't have any forced thunk pairs. Because if we were to have interpret n as x here, then we would have m applied to the thunk of force of x, which we can't have. These encodings do respect reduction of call by value and call by name. The new substitution is needed, though, to the call by name value, as you remember from the self-returning term. So what we also have here is the calculus lambda-bar-mu-mutilde. This is Herbert and Curian's calculus that models call by name and call by value reduction in a different way to call by push value. This has three categories of expressions. It has commands, which has a term on the left-hand side and an environment on the right-hand side. It can also be seen as a kind of abstract machine, as we'll see later. Terms are just variables and abstractions, but we also have this mu abstraction, which takes a context and returns a command. We have an environment, which can be an environment variable, which we denote by Greek letters here. It could be a stack of a term onto another environment, or it can be this mutilde abstraction, which takes a term and returns a command. We have our reduction rules. So the mu reduction rule, as we can see, just kind of does what we'd expect. It takes, if a mu is in the left-hand side of a command, it will take the right-hand side, it will substitute the right-hand side's environment, and same for mutilde, but in the reverse. The interesting one here is how lambda is done. So if we have a lambda term in the left-hand side of a context and a stack in the right-hand side, we don't immediately substitute it, as you might think. We, in fact, just pop the term off the stack and put this kind of mutilde, so we create this mutilde term through lambda reduction in the right-hand side, which, if we reduce it immediately, will apply T2 to mutilde. So we can see a critical pair here is if we have a mu on the left-hand side and a mutilde on the right-hand side. Which one do you reduce first? And in fact, both of these reductions are not confluent, so you might get a different result depending on which one you reduce first, which is why it's so interesting here. The rule lambda here, because it doesn't immediately reduce, we can actually see the strength here to model both call by name and call by value reduction. So we have lambda-mu-mutilde values, which kind of correspond to lambda values, variables and abstractions, and we have what we call stacks, which has an environment variable and this t on top of a term on top of an environment, which I'm calling a stack as well. So a stack could just be kind of a finite number of terms on top of variables. Call by name reduction limits the mu reduction rule to stacks. So say we had a critical pair of mu and mutilde, then we will always run the mutilde in call by name reduction of the lambda-bar-mu-mutilde calculus. Call by value does the opposite. We limit the mutilde rule. So if we have a critical pair of a mu on the left-hand side and a mutilde on the right-hand side, we will always run the mu. Both of these reduction strategies only run terms and never context. We can only run in the left-hand side of a command or under a mu abstraction in both of these reduction strategies. So say we had a lambda abstraction and we expanded that into popping the term into the left-hand side and putting a mutilde in the right-hand side, then our call by value reduction, we would reduce our term in the left-hand side until it produced one of these values, and then we would apply our mutilde. And then if we had call by name, we just immediately run the mutilde so that we'd substitute it in. Our type assignment for the lambda-bar-mu-mutilde can be seen as a kind of variation of the implicative classical logic, so Gensen's sequent calculus. Indeed, we can type Peirce's law, and this is the lambda-bar-mu-mutilde term that represents it. We just have, so the cut rule here is what really kind of exemplifies this correlation between them. But more interestingly, we can now interpret our calculus of delayed reductions into lambda-bar-mu-mutilde, which kind of relates the call by name and the call by value reduction strategies between them. So regularly, we basically interpret variables as variables. We get rid of all the forcing and thunk markers and the ret marker. The more interesting thing here is what we do in terms of application and sequencing, which, according to our reduction rules in the calculus of delayed reductions, that's what actually produces new results. This is what our base reduction rules are. So, interpreting an application, we put the left-hand side of an application in the left-hand side of a command, and we put our value on a stack. For sequencing, we put our first sequence in the left-hand side of a command to run, and then we put our second sequence under a mutilde abstraction in the right-hand side, ready to be substituted. So the left-hand side is ready to be substituted for x once it's reduced. This reduction, modeling of the reduction rules of CDR, actually takes place in the call by name reduction of lambda-bar-mu-mutilde, where we can only reduce mu's when we have not a mutilde on the other side. This is because to reduce application here immediately, we have to be able to reduce our mutildes immediately. Otherwise, we'd run our value, which might be a thunked computation, which we do not want to run. We want to immediately substitute it. For type assignment, we also just get rid of all our type markers for thunks and forces. So we can also, Levy also explains an abstract machine for call by push value, this CK machine. And this is kind of what originally brought us to comparing call by push value and the lambda-bar-mu-mutilde calculus in the first place. Essentially, we are going to define an evaluation of like an abstract machine state as this pair of a call by push value term and an evaluation stack. You can kind of notice a kind of similarity between the terms of lambda-bar-mu-mutilde and these evaluation stacks. So this kind of just has the original ones, where we can apply a value that's popped on an evaluation stack to an abstraction. If we sequence something, we can pop the sequenced value, the sequence computation along with the substituted variable onto the stack. Returning pops this special syntax off the stack. Application just pops the value on the stack. But notice in the last rule that forcing and thunking doesn't interact with the stack whatsoever. It's just this kind of rule that does itself. It's just this syntactic rule to get rid of these markers itself. It doesn't interact with any kind of evaluation context. So we can use lambda-bar-mu-mutilde as a stack machine for calculus, for call by push value. So we can interpret these evaluation stacks as a lambda-bar-mu-mutilde environment. Just E, our regular stack is just some kind of variable. We have our stacks of call by push value values as a lambda-bar-mu-mutilde stack. But here's where the interesting one is. X equals this context hole sequenced with n actually is a mutilde, which kind of makes sense. We have an environment which takes a variable and returns a command which runs another substitution in the rest of the stack, which is exactly what mu-tilde does. And then we just have our regular stacks, which substituting, basically copying this syntax here and using the original interpretations we made from CDR into the lambda-bar-mu-mutilde-calculus. It was this exact similarity that we can see here that originally was the inspiration for our entire paper, for us examining how call-by-push value works in the lambda-bar-mu-mutilde-calculus and realizing that we don't really have a way to model this forcing and thunking, which got us interested in why that was necessary in the first place. We can show that if the CK stack runs, then runs to another CK stack, then their interpretations do eventually run to each other. So this does respect reduction in that way. So in conclusion, we've defined a calculus based on Levy's definition of call-by-push value. We've shown that tweaking term substitution and using pattern matching in the interpretations, the call-by-name and call-by-value reduction in the lambda calculus are respected by reduction, not just an interpretation of it or by equality. We established a strong relation with lambda-bar-mu-mutilde, showing using this CK machine approach. And because to model call-by-push value reduction in lambda-bar-mu-mutilde, we need to use the call-by-name fragment of lambda-bar-mu-mutilde. We show that call-by-push value reduction is actually based on the call-by-name reduction. Since then, we've added call-by-value reduction to call-by-push value, adding a let construct, and we gave the lambda-bar-mu-mutilde the call-by-push value treatment, and showed a strong relation between the two, mapping call-by-name to the call-by-name fragment of the call-by-push value to call-by-name and lambda-bar-mu-mutilde, and vice versa for call-by-value. Next, we will see if thunking, forcing, and return are really necessary. Questions?
Thank you very much. So, are there any questions? Yes, please. Yeah, just for recording.
The one is about in your call-by-push value framework, why you decide to keep variables as values?
So you're suggesting that we could have put variables as computations instead? Perhaps.
I mean, why do you need to do that?
Yeah, I mean, why do we need to have the distinct sets of values and computations in the first place? That's an interesting thought. I think that we wanted to keep as close to call-by-push value as possible, the syntax of that, changing call-by-push value as little as possible so that we could get the results that we needed, which was correct call-by-name reduction. But you're right, we could create an entirely new calculus which gets rid of these distinct sets of terms and just has a subset like the lambda calculus does of values.
And another question is, so now that you have a good correspondence by using your new translations, have you used these translations to infer or derive properties from for call-by-name and call-by-value from the ones for call-by-push value or vice versa?
Not yet, I don't think so.
I don't understand the question.
So the question is, now that you have a good correspondence between reduction in call-by-name and call-by-push value, do you use this correspondence to get deep results of preservation of some kind of property? For example, you can infer different property, for example, confluence. Let's take an easy one. You can infer confluence for call-by-name and call-by-value using confluence for call-by-push value. That's just an example.
So first of all, the confluence issue doesn't exist in call by push value because you can always only reduce one thing. There's only and there are no diverging reduction paths in call by push value, and so the extension that we have when we add call by value, that's when we have to look at confluence. Now we have an extended reduction system with diverging paths, and we can do that. So I think the properties that Levy shows for his interpretations are very shallow. He doesn't really investigate anything deeper. So what the paper basically does, it fixes that approach. I think it's very. I think the strength of the paper is that with very minor changes, not really. For example, Levy talks a lot about semantics in his paper. That's all preserved. That we don't touch that at all. The only thing we do is change the substitution, and that's everything works. Yeah.
Okay. Other questions? Oh, yeah.
Yes. You changed both the substitution and the translation to call by name and call by push value. How do those things interact? So do you still have the property that if you have an open term, then substitute and translate, it's the same as translating first and then substituting?
Yes, yeah. So we do in the paper prove that substitution itself is preserved from, the interpretations in the lambda calculus. So substitution in the lambda calculus is substitution in call by push value, even with this new substitution rule. So we do get all those nice properties that you do get from like our interpretation is not like, just saying, oh, well, it's this and then it's this and then, it kind of works. No, it is a proper, nice interpretation here that is luckily one-to-one now, and other than this kind of set of equivalence classes.
Yes, thanks.
Okay, so thanks again for the discussion.